Every instructional design faces the same biological constraint. Working memory is a finite resource. Push too much information through at once, and the system overflows. Cognitive load theory breaks this mental bandwidth into three distinct components. The first is intrinsic load. This is the baseline difficulty of the material itself, the inherent complexity of the subject you are trying to learn. The second is extraneous load. This is the friction caused by the format. It's the unnecessary mental effort spent navigating a clunky interface or deciphering poorly structured instructions. The third is germane load. This is the productive effort. It is the cognitive work required to construct mental models, encode patterns, and learn the material. The math here is unforgiving. If a poorly designed format demands too much extraneous load, those background processes consume the remaining bandwidth. Working memory reaches absolute capacity, and the actual process of learning stops immediately. For decades, determining when a learning task became too difficult relied on subjective tools. Researchers would have users complete a task and then ask them to fill out a questionnaire rating their perceived mental effort. This chart compares a flat, smoothed-out subjective average against the highly volatile reality of continuous cognitive strain. A post-task survey misses the sharp, instantaneous spikes in mental effort that occur while the user is performing the task. When you attempt to build a responsive learning environment based on a user's retrospective memory of their own frustration, the data is incomplete. The result is an instructional design that targets the wrong moments of difficulty. To capture these transient events, the design process needs an objective layer that measures the hardware limits of the brain directly as the task unfolds. The tool used to capture that raw data is the electroencephalogram, or EEG. It allows us to record the continuous electrical oscillations of the brain during learning. Complex cognitive events, like memorizing a sequence or solving a puzzle, don't activate a single brain region. Instead, they modulate multiple superimposed frequency bands across the neural landscape. For measuring working memory, we isolate two scalp locations: the middle frontal region, FZ, and the central parietal region, PZ. At FZ, theta wave amplitude spikes as mental effort increases. Conversely, at PZ, alpha wave amplitude decreases under mental strain. This divergent wave behavior, theta scaling up while alpha scales down, is a precise neurophysiological signature. It indicates when a working memory system is hitting maximum load. To make this biological data useful for research, it must be converted into a computable model. A framework derived by Holm and colleagues quantifies these oscillations. They developed the Cognitive Load Index, or CLI. It's a mathematical ratio dividing frontal theta power by parietal alpha power. To account for individual resting states, this active task load is divided by the user's initial baseline observation. This provides the relative CLI, a normalized metric comparing active task load against the baseline, allowing the data to scale for any specific user. This ratio provides a way to quantify mental strain, turning invisible cognitive effort into an objective, computable value. To test this metric, researchers at the Technion Israel Institute of Technology conducted a controlled experiment on how instructional formats affect cognitive load. They selected 10 participants and separated them into two groups, mathematically matched for age and pre-tested for spatial reasoning abilities. The task required significant spatial memory. Participants watched an instructor fold a paper crane, memorized the sequence, and then physically repeated the steps themselves. One group watched the demonstration on a flat 2D video screen. The second group learned the steps while immersed in a 3D virtual reality environment. The session was broken into 4 20-second observation periods, with physical folding occurring between each viewing. A critical detail in the task sequence is that steps 2 and 4 are recognized by experts as the most spatially complex folds in the crane's construction. This isolates the experimental variable. We have matched brains performing an identical task, separated only by the dimensional format of the medium. This chart displays the EEG output from those observation periods. The x-axis represents the 4 sequential learning stages, while the y-axis tracks the intensity of the relative CLI. These solid blue lines plot the cognitive load of the participants who learned inside the 3D virtual reality environment.
Across the sequence, the 3D VR group registered a mean relative CLI of 0.79. The dotted red lines track the participants who learned the same steps via the flat 2D video interface. Their data is significantly higher, registering a mean relative CLI of 1.26. The real value of the metric is visible at periods 2 and 4. Here, the chart reveals sharp, pronounced peaks in the 2D group's data. For an identical task, the flat 2D interface forced the brain to work nearly 60% harder over the duration of the learning sequence. Because these were the hardest folding steps, the EEG successfully captured the localized spikes in mental effort that a post-task survey would miss. The 2D group suffered high extraneous load because their working memory had to mentally translate a flat image into a three-dimensional spatial reality before they could learn the fold. The 3D VR format offloaded this spatial translation from the user's brain into the environment, freeing up working memory for the germane load of actual learning. The technology used in this research is becoming increasingly accessible. Low-cost wireless EEG headsets are transitioning out of the laboratory and into the consumer hardware market. This enables closed-loop brain-computer interfaces, systems where the software actively monitors the user's neurological state in real time. Future educational technologies could use the relative CLI to continuously adjust data velocity. If theta spikes, the system can simplify the interface. Once alpha recovers, it can reintroduce complexity. Future instructional design will involve linking the computational power of the interface directly to the real-time bandwidth of the human mind.